All right, today we are going to be talking about harmonic motion. Harmonic motion is a very, very important topic to understand because a lot of things undergo harmonic motion. So today we're going to be talking specifically about masses oscillating on springs. But remember, a mass oscillating on a spring is analogous to a lot of other things. So the reason we really want to understand masses oscillating on springs really well is the type of motion they do is the same as a lot of other things in the world. So if we can understand a mass oscillating on a spring, if we can understand harmonic motion, we can also understand things like a pendulum oscillating back and forth, or a ball rolling back and forth in a curved candy dish. All right, just lots of things undergo harmonic motion that are analogous to a mass on a spring. If you take a plastic ruler and flick it and the end vibrates, as long as the vibrations are not too big, what it does is analogous to a mass on a spring. It's harmonic motion. If you take a wine glass and flick it, the vibration it does is analogous to a mass on a spring. It will undergo harmonic motion. And it turns out, as we will learn in another video lecture, things like sound waves traveling through the air or waves traveling down a guitar string or ocean waves, those are all strongly coupled to harmonic motion. So if we can understand harmonic motion, it's going to help us with a lot of different things. So let's talk about a mass on a spring now. Well, actually, before we talk about a mass on a spring, let's talk about why so many things are like a mass on a spring. So here I've plotted the force as a function of displacement from equilibrium for an ideal spring which obeys Hooke's law, right? And as I pull the spring away from equilibrium, there's a force that tries to pull it back. And as I squish the spring and compress it away from its equilibrium length, there's a positive force that tends to push it back. So whichever way I go, there's a force in the opposite direction trying to bring the spring back to its equilibrium length. And according to Hooke's law, that force is just a line. Well, in addition to thinking about the force, I can also think in terms of potential energy. If I integrate the force to find the potential energy, I get a parabola. As you'll recall, the potential energy stored in a spring is 1/2 kx squared. So I get a parabola here. All right? And you can kind of think of harmonic motion in terms of energy. Imagine I have some block and I bring it up a hill and it slides down the hill. When it gets to the bottom, it still has energy, still has kinetic energy, so it slides up the other side, and then it comes to a stop and it slides back. So you can kind of think of a mass on a spring kind of like something sliding in a gravitational potential on a hill. All right? So basically, here is the force and the potential energy of our ideal spring, which will undergo harmonic motion. But as you recall in a previous video, we made up kind of a non-ideal spring force. We said, imagine a spring, actually its force looked like this, right? We just made this up and said, well, what if we had a non-ideal spring, did something like this? And our comment was, well, if you focus on the area close to the equilibrium point, it still looks like a line. So as long as you don't oscillate very far from equilibrium, you're still going to get the same oscillation you would have gotten for an ideal spring undergoing harmonic motion. And if we look at the potential energy you get by integrating this force, you can see it's different from what we get for an ideal spring, but here near the bottom, it's the same. So the point is, even if we have a non-ideal spring that does not obey Hooke's law, for small amplitude oscillations, for small displacements from equilibrium, it will behave like an ideal spring. Well, what if we had some other thing that was entirely not like a mass on a spring, like a wine glass or a ruler vibrating, right? Well, in that case, if we have some weird force as a function of distance, as we move away from an equilibrium point, as long as we don't move too far, it looks like a line. And the potential energy at that potential minimum, at the equilibrium point, looks like a parabola as long as we don't move very far. So just about anything oscillating with small amplitude, small displacements, is going to oscillate just like a mass on a spring. So let's understand what happens with a mass on a spring, since it's analogous to so many different things. Well, the force of an ideal spring is Hooke's law, right? Minus kx. So the minus sign tells us that as we move in the positive x direction, the force tends to push us back towards equilibrium. If we go in the negative x direction, we get a positive force that, again, tries to push us towards equilibrium. This constant k is known as the spring constant, and it basically tells us how stiff our spring is. If we have a very stiff spring, a little displacement will make a lot of restoring force. Okay, now force is equal to mass times acceleration. So if this is the force, I get the acceleration just by dividing this by the mass of the mass on our spring. So there's the acceleration of a mass on a spring. Well, of course, acceleration is just the second derivative of position with respect to time. So I can replace acceleration with just the second derivative of x with respect to time. And now what I have is a differential equation. All right? I have knowns, the spring constant and the mass, and then I have this thing here, x. X is a function of time. We want to know how x changes with time. So the trick here is we have to solve this differential equation. In other words, we need to find this function x, which is a function of time, that when I plug it into this equation, it works. All right, so there are many different ways to solve a differential equation, but the basic idea is solving a differential equation is finding this function x that satisfies this equation. Well, what do I mean it satisfies that equation? Well, let me illustrate that by giving the wrong x. Let's imagine I have this differential equation I want to solve, and I decide that the solution is that x is equal to a constant times t cubed. All right? How do I see if that actually solves the equation? Well, what I do is I just plug it into the equation and I see if it makes sense. Well, to plug it into the equation, I need to know its second derivative. So the first derivative of x with respect to time is just going to be 3 times a times t squared, where, again, a is a constant. And the second derivative is 6 times a times t. So now I will plug that in for the second derivative of x, 6 times at, and then I have minus km times x, and for x, I'm just going to plug in a times t cubed. Well, the a on both sides cancel, and one of the t's, and this simplifies to this equation here. Does this equation make sense? 6 is equal to negative k over m times t squared. This implies that there's only one time, right? The time has one value, but time doesn't have one value. Time goes on, right? I take my spring on my mass and I stretch it and I let it go, and x changes with time. And time, I can evaluate this at any time, but this is saying no, time is just one number. That doesn't make sense. So this is wrong. And x equals at cubed is not the solution to this equation. All right, so what is the solution? Well, as I mentioned, there are many different ways to try and solve differential equations. Some differential equations are easy to solve, some of them are very difficult to solve, some of them don't even have analytic solutions. They can only be solved numerically. But this one, to solve this one, we're going to use a method of just guess and check. We're going to look at it and think about what the solution ought to look like, write down a guess, and see if it works, okay? So if I look at this equation, what it's telling me is that if I take two derivatives of x with respect to time, I'm going to get x back times a constant. What functions can I take two derivatives of and get the same thing back times a constant? Well, one function that does that is sine. If I take the derivative of sine, I get cosine. If I take the derivative of cosine, I get negative sine. So I get sine back times a constant. But let's make our solution a little more general than just a sine. Let's make it a sine times a constant, so I can make the sine wave oscillate with bigger or smaller amplitudes. And then, of course, time has units. I need something without units to put into my sine, right? Sines eat radians, not seconds. So I'm going to put a constant times time. I'm going to use omega to be the constant. And then I'm going to allow another constant in there that I'm going to call phi. All right, so I'm going to guess that my solution to this equation is a, which is a constant, times sine of omega t, where omega is a constant, plus phi, where phi is a constant. Now, how do I check and see if my guess is correct, if this really is a solution? Well, I'm going to take a derivative of that. When I take a derivative, the sine becomes a cosine, and I get out a factor of omega. I take another derivative, and cosine becomes minus sine, and I bring out another factor of omega. So now I have the second derivative of x with respect to time, and I'm going to plug that into my equation for this. I'm going to plug this in for x, and this is what I get. All right? Now notice that the a's cancel out, and the sine omega t plus phi terms on both sides cancel out, and I'm left with negative omega squared equals negative k over m. Does that make sense? Well, what that tells me basically is this is a solution as long as omega is equal to the square root of k over m. So this omega here in our solution, it depends on the spring constant and the mass, all right? But as long as I let omega be equal to that, I've got a solution. So I started with this force, and I found that this is the oscillation that our mass will do. Now, A could be any constant, and it's still a solution, right? A didn't matter, and phi didn't matter. But omega has to be equal to the square root of k over m. And there we have our solution. Now, since harmonic motion involves sine waves, I want to just take an aside here and talk a little bit about sine waves, help you get more familiar with sine waves. Now, of course, a cosine is just a sine wave with a phase shift. So a cosine is just sine with a different phi here. So when we talk about sines, we're really talking about cosines as well. Okay, as you recall, a sine is just if I have a unit circle and I draw a vector from the center of the circle out to the edge that makes some angle relative to the x-axis, right? The sine of that angle is just the length of the y component of that vector on the unit circle. All right, so if I start with 0 angle, sine of 0 is 0. So here's my circle over here, and I'm plotting sine in the y-axis as a function of theta on the x-axis over here. And as I increase theta, sine of theta gets bigger. Once theta becomes 90 degrees, I reach the maximum value for my sine. Sine of 90 degrees is 1. And if I increase the angle more, then sine of theta starts to come down. And when I plug in 180 degrees, or pi radians, my sine has returned to 0. As I continue to increase theta, now the y component of this vector becomes negative, so sine of theta becomes negative. And then when I get to 270 degrees, or 3/2 pi, my vector is pointing straight down, and sine of theta reaches its maximum negative value of -1. As theta continues, sine of theta gets less negative, and eventually, when I've done a complete circle, when theta is equal to 360 degrees, or 2 pi radians, I've returned to my original starting point. What happens is I increase my angle even more. If I increase my angle, if my angle is 360 degrees plus 45 degrees, I get this point right here. And you see what happens is the sine just repeats itself. Sine is what we call a periodic function. It repeats over and over again. So every 360 degrees, it just repeats, right? So 360 degrees plus 90 degrees, I take the sine of that, I'm going to get 1, right? And as I just keep increasing theta, sine just oscillates. Sine of theta just oscillates. So sine of theta is this curve here on the left that you see, and that's what a sine wave looks like. Okay, so now knowing what a sine wave looks like, we can plot the position of our mass on a spring as a function of time. We can predict it. It's just going to be a sine wave. Okay, so now there's some terminology we use when we talk about harmonic motion and sine waves. So let's go over that. So if my mass is oscillating according to this equation here, right, where A is a constant that is arbitrary, and phi is an arbitrary constant, and omega is, again, the square root of k over m, it turns out that A, this constant A, that's the biggest our x ever gets. Right? So here's x equals 0, A is the biggest it gets, and that constant A is what we call the amplitude. For a mass on a spring, the amplitude has units of meters. But for other things that oscillate, it may have different units. For example, for a pendulum, we can say that the pendulum, its angle is oscillating, and so A is the maximum angle it gets to, and it will have units of radians. Or if I had a light wave that was oscillating, the electric field in a beam of light oscillates sinusoidally, and its amplitude will be in units of electric field, volts per meter, all right? Now, this is also the amplitude right here. So the amplitude A is not just the biggest the sine wave gets, it's also the most negative that our sinusoidal wave gets. Okay? Now, this distance from peak to peak is what we call the period, t. So the period is the time it takes for the wave to repeat. Now, if I go from one peak to one peak, the time between them is one period. One trough to one trough is also one period. Or one crossing zero as we come down to the next crossing zero as we come down is also a period. Or from here to here is a period. A period is simply the time we have to wait before the sine wave repeats. So if I see where the mass is, how fast it's going, and in what direction, one period later, it will be in that position again, going at the same velocity in the same direction. 2 periods later, it'll be at the same spot, going in the same direction with the same speed. All right, now if I take 1 over the period, I get what's known as the frequency. So the period has units of seconds. The frequency has units of 1 over seconds, or hertz. So if the period is the time it takes to do one cycle, the frequency is the number of cycles done per second. So if it takes 2 seconds, if the period is 2 seconds, it takes 2 seconds for the motion to repeat. That's 2 seconds per cycle, or 0.5 cycles per second. So the frequency would be 0.5 per second, or 0.5 hertz. If the period was a quarter of a second, then that would be 4 cycles per second. So the frequency would be 4 hertz. Now, the frequency is how many cycles per second. There are 2 pi radians in each cycle. So we're going to define something called the angular frequency, omega, to be 2 pi times the frequency. So if my mass oscillates 1 cycle each second, that's a frequency of 1 hertz, which would be 2 pi radians per second. So if I take the frequency multiplied by 2 pi, I get omega, the angular frequency. Now, previously we used omega to represent angular velocity for something which is rotating, and it turns out there's a reason why we use the same symbol. There's a reason why they have the same units, radians per second. And at the end of this presentation, we'll talk about the connection between oscillation and rotation. But for now, just know the angular frequency is 2 pi times the frequency. The frequency is cycles per second, angular frequency is radians per second. Now, the phase of our oscillation, or the phase of our sine wave, is just the argument inside, the omega t plus phi, and it has units of radians. All right, so if I say the phase of the oscillation is 0, that means, omega t plus phi is 0, and we're taking sine of 0. And this constant phi we call the phase shift. It also has units of radians. Okay, so now we understand that if my force is Hooke's law, or if I have any system where the force is just minus some positive constant times the displacement from equilibrium, the solution for the motion is just a sine wave with an angular frequency of k over m. So this omega here is square root of k over m, and that's what we call the angular frequency, the number of radians per second in the oscillation. Well, if I take 2 pi times the frequency, I get the angular frequency. So if I want to get the frequency, I just take the angular frequency divided by 2 pi. So I go from radians per second to cycles per second. But since omega is just the square root of k over m, we know that the frequency of oscillation, the number of cycles per second, is 1 over 2 pi times the square root of k over m. And 1 over the frequency is the period. So the period is just 2 pi times the square root of m over k. All right. Now, we know about the position as a function of time. What's the velocity and acceleration of our mass at any time? Well, if the position is a sine omega t plus phi, the velocity is just the time derivative of that. So I take the time derivative and I get omega a cosine of omega t plus phi. So that tells me that the biggest the velocity ever gets in the oscillation is omega times A. Does that make sense? A bigger oscillation amplitude would mean it has to oscillate faster for the same given frequency. But the velocity also depends on the frequency. For a given amplitude, if you oscillate 10 times per second, your velocity has to be 10 times bigger than if you oscillate at the same amplitude, 1 cycle per second. So the velocity, the maximum velocity, is proportional to the frequency, which means it's proportional to the angular frequency. And it turns out the maximum velocity is just omega times the amplitude. To find the acceleration, I take one more derivative with respect to time, and I get this. So once again, the acceleration is the velocity is 90 degrees out of phase with the position, right? Position goes as sine, velocity goes as cosine. Acceleration is 180 degrees out of phase with the position, right? It's a sine, but there's a minus sign in front. And that makes sense because when we're at our lowest point, the acceleration is upward, right? When we're at our lowest point, when x is the most negative, the spring is pushing upward with the most positive force of the cycle. That's when we get the maximum acceleration. And the maximum acceleration, the amplitude of the acceleration, is omega squared times A. And again, that makes sense. Bigger amplitude means more acceleration. Bigger frequency for the same amplitude means more velocity. And then more velocity means at a higher frequency, we need even more acceleration. So the acceleration scales as omega squared times the amplitude. Okay, so here's a problem we can work. I hang a weight with a mass of 220 grams on the end of a spring with a spring constant of 378 newtons per meter. The other end of the spring is fixed to the ceiling. Then I pull the weight down, stretching the spring 3 centimeters from its equilibrium length, and I let go. What will the position and velocity of the mass be 0.5 seconds later? Ignore the effects of gravity. Okay, so here are the givens. I'm given the mass of the mass, the spring constant of the spring, the distance that I pull the spring before I let it go, and then I want to know the position and velocity at a time of 0.5 seconds after I let go. Okay, so we have an equation. This is the position. And I would know the position if I knew what A and phi were. I do know what omega is because I'm given K and M, and I know that omega is the square root of K over M. Now, knowing omega, I can plug in numbers. I can find omega, and from that I can find the period, right? And if I just plug in the numbers, it says that the period is going to be 0.151 seconds. So 0.5 seconds is a little more than 3 periods. So our mass is going to oscillate a few times before the 0.5 seconds is up. Okay. If I take the derivative of my position equation, I get the velocity equation. And so once again, if I know omega, if I knew A and I knew phi, I could just plug those in with my time of 0.5 seconds, and I could get the position and velocity at that time. Well, how do I find A and phi? Well, I've got some initial conditions. I know that at time t equals 0, the mass is not moving. I stretch it out and I let it go at time t equals 0. So that means the velocity has to equal 0 at time t equals 0. But at time t equals 0, this is 0, and the velocity is just omega A times cosine of phi. Well, omega is fixed, right? It depends on K and M. I can't set A to 0, otherwise the thing doesn't oscillate, right? And so what I've got to do is I've got to pick phi correctly so that cosine of phi is 0, all right? Because that will ensure then that I have a solution that has 0 velocity at time t equals 0. Well, cosine is 0 for plus or minus pi over 2 radians. So those are good choices for phi. That gives me phi, but what is A? Well, I have another condition. At time t equals 0, I've pulled the mass down by an amount h and I let go. So at time t equals 0, y has to equal negative h. But at time t equals 0, all right, we get y is just A times 0 plus our phi, which is plus or minus pi over 2. But sine of pi over 2 is 1. Sine of negative pi over 2 is negative 1. And so A must be plus or minus h. So let's choose to go with phi of negative pi over 2 and let a be h. And now I've got a solution that fits my initial conditions, the starting point of our mass on a spring. Now I could have chosen plus pi over 2 and let a be negative h, would have worked out the same. So there's my position and there's my velocity, and it's just, I started with the generic solution to the mass on a spring equation, and I chose a and phi such that it had the right values at time t equals 0. Now I can just plug things in, right? If I take the position equation, I just plug in h, I plug in k over m for omega, and then I plug in all the numbers for all of these things, and I find that its position at time 0.5 seconds is 0.901 centimeters. If I actually plot this solution as a function of time out at 0.5 centimeters, there you see, there it is, about 0.9 centimeters. All right? So it goes from negative 3 centimeters up to 3 centimeters and oscillates, and at time 0.5 seconds, it happens to be right there at 0.901 centimeters. I can also calculate the velocity by plugging things into the equation we found for velocity. And when I do that, I get 1.19 meters per second. And then again, when I plot the velocity, it starts out at a velocity of 0, then it gets accelerated upwards by the spring, then it turns around, and it oscillates. And after just over 3 oscillations, we stop right here at 0.5 seconds at a velocity of 1.91 meters per second. But what about gravity? In this previous problem, we ignored gravity. What if I have a spring, a mass on a spring, but gravity is holding it down? Well, remember, force is equal to mass times acceleration. So if I want to include gravity, now my acceleration is force divided by mass, but that force is going to be Hooke's law, but also minus the force to gravity, downward. So that means my differential equation now looks like this. What solves this equation? Well, if I plug in my previous solution, I'm going to be left with this minus g out here that doesn't cancel out, right? If my previous solution makes this equal to that, well, let's just add a constant to our sine wave, right? Because when I add a constant, that constant goes away when I take 2 derivatives, but it's still left over here and maybe can cancel out that constant. So that's the solution I'm going to guess if I have gravity. I take 2 derivatives of it and I get this. I plug everything, I plug this in for here, and I plug in y for this, and then I solve my equation, and once again, this g here makes it so I can't cancel things. But if not for that g, I could cancel the a and I could cancel the signs. So what I'm going to do is I'm going to cancel them out anyway and make sure q is just big enough to cancel out the g when I do. So that tells me this is a solution as long as omega is equal to the square root of k over m, and as long as this is true, right? So that we can cancel out the g. So I solve that for q, and I get that, so there's my solution. It's just a constant, an arbitrary constant a, times sine of omega t plus phi minus mg over k, where a and phi are arbitrary constants, and omega is, of course, the square root of k over m. Well, notice, if I have just a mass sitting and not oscillating, just sitting there in equilibrium, equilibrium is when the forces cancel out. So I have gravity downwards, and I have minus ky for the spring pulling upwards. So if I have a mass just sitting on the spring, how far does that mass sit from the equilibrium point, the unstretched point on the spring? It turns out it's just precisely equal to that. So our solution is basically just, hey, it just oscillates like a mass as if there was no gravity, but it oscillates not around the point where the spring is relaxed, but about the point where the spring force cancels gravity. So it still undergoes harmonic motion. Pretty groovy, huh? Okay, now let's talk about the energy in a harmonic oscillator. Now the energy is going to be constant because the only force involved is the spring force, which is a conservative force. So as my mass oscillates on the spring, the total energy of the mass in the spring, which is the kinetic energy of the mass plus the potential energy of the spring, will be constant. Now, the kinetic energy of the mass is just 1/2 mv squared, and the potential energy of the spring is 1/2 kx squared, and the sum of those will be a constant. So as I plot the potential energy, the kinetic energy is just going to be the total energy minus the potential energy at any given displacement. Now there's a point for a given, once I choose the total energy, there's a point where the kinetic energy goes to zero, and that's the turning point. So the potential energy is really big over here. There's a force pushing it inward. As we go inward, it accelerates. And at the equilibrium point, where the net force on the object is zero, that's when it has the most kinetic energy. And then as it moves out, the spring takes up energy, the kinetic energy drops, and right where the kinetic energy gets to zero, that's the turning point on the other side. So here I've plotted a sine wave. Here's my mass that's oscillating with time. And down here, instead of plotting energy as a function of position like I did here, I'm plotting energy as a function of time. And you can see when the mass is at its most positive position, that's when I have the highest potential energy and my kinetic energy is zero. Then as my mass comes down and crosses x equals zero, that's when I have no potential energy and I have maximum kinetic energy. Then my mass comes down, and right here where it's at its most negative point, again, I reach a maximum in the potential energy and zero in the kinetic energy. And as it oscillates back and forth, you're just swapping kinetic energy with potential energy such that the sum of the two is a constant. So here's a problem we can work now. I hang a weight with a mass of 220 grams on the end of a spring with a spring constant of 378 newtons per meter. The other end of the spring is fixed to the ceiling. Then I pull the weight down, stretching the spring 3 centimeters from its equilibrium length, and let go. What will the position and velocity of the mass be when it reaches its maximum kinetic energy, and at what time will it first reach it? Now I'm going to ignore gravity again because we said, well, gravity is just like moving our equilibrium point. It doesn't really matter that much for this problem, okay? So here are my givens. I'm given the mass, I'm given the spring constant, and how far I pull it down before I let go. And what I'm trying to find is the position and velocity when it has its maximum kinetic energy, and at what time it first reaches that point. Well, here's the, quote, simple but not easy way. Simple meaning straightforward, just plug things in, but it won't be as easy as if we were clever. So I know my initial conditions, right? At time t equals 0, y is negative h, and the velocity is 0. And so I take my generic form of the equation, and I'm going to find what a and phi need to be for my initial conditions. And then once I have my equation for y, I can find out what is y when I reach my maximum kinetic energy, what is v when I reach the maximum kinetic energy, and at what time I first reach maximum kinetic energy. Okay, so here's my equation. Omega is k over m, and I apply my initial conditions. Initial velocity 0, initial position is negative h, just like we did before, and we decide, oh, y is just h sine of omega t minus pi over 2, and velocity is omega h cosine of omega t minus pi over 2. So now I have these equations. I can just say, well, what's the biggest the velocity gets? Well, if I look at this, right, I've got my cosine. The biggest cosine ever gets is 1. So my maximum velocity is just omega times h, which is square root of k over m times h. Plugging the numbers in, I get 1.24 meters per second. Okay? Well, now that I know the maximum velocity, all right, the maximum velocity happens when this argument here is 0, or an integer times pi, right? That's when I get my maximum velocity. So now we just need to figure out at what time do I reach those maximum velocities. Well, I'm going to take the negative pi over 2 to the other side, add pi over 2 to both sides, and then I'm going to factor out a pi over 2. So I just end up with omega t max k is pi over 2 times 2n plus 1. So if I plug in a value of n, I will find a time when I'm at a maximum kinetic energy. Well, let's just divide both sides by omega, and now I have my equation that tells me the times at which I reach a maximum in kinetic energy. Well, n can be any integer, but we wanted the time when we first reach a maximum kinetic energy. So what should m be to give us the smallest t max k that's not negative? Well, it turns out n equals 1. So if I plug in, n equals 0, since we just have a 1 here. So if I plug in n equals 0, I get this, and of course, omega is the square root of k over m. I plug in the numbers, and I find the time at which it first reaches its maximum kinetic energy is 0.0379 seconds. Okay? So now we found the maximum velocity and the time at first, or the velocity at the maximum kinetic energy and the time at which it first reaches it. Now we're going to look and say, well, this is when we reach our maximum kinetic energy. What happens if I plug this into my y equation? If omega t minus pi over 2 is n pi, well, sine of n pi is 0, so that tells us that the position at which we reach the maximum kinetic energy is when we're at the equilibrium position, when the displacement is equal to 0. Okay, now let's do it the really easy way. The really easy way is, what is our trick that often makes hard problems really simple? Conservation of energy. All right, so the energy of our mass on our spring is just the kinetic energy plus the potential energy. 1/2 mv squared plus 1/2 ky squared. All right, so the mass has a certain amount of energy. When does that mass have the maximum kinetic? It has the maximum kinetic when it has the minimum potential energy. And where does it have the minimum potential energy? When y is equal to 0. Okay, so we know that the y position where we get the maximum kinetic energy is 0. So now we just have to say, well, look, when I pull my mass, it's not, and let it go. Right when I let it go, there's no kinetic energy. It's not moving, so it's all potential energy. So the energy when I let it go is this. The energy, the final energy, the energy when it reaches its maximum kinetic energy is when there's no potential energy, so it's just kinetic energy, but E initial has to equal E final, so this equation must be true, and I can solve and find the maximum kinetic energy, which is exactly what we found doing things the hard way earlier. So now I know the position at which I get maximum kinetic energy, I know the velocity when I have maximum kinetic energy. The last thing I need is the time. Well, if you'll notice, if I start down here at minimum y, when I reach y equals 0, that's 1/4 of a total cycle. So the time it takes to first reach that point where we have the maximum kinetic energy is 1/4 of the period. But the period is just 1 over f, and f is omega over 2 pi, and we get exactly the same equation we got when we were doing things the hard way. All right, so hopefully this helps you work with simple harmonic oscillators. But before I go, I wanted to point out the similarity of rotation and harmonic motion. So what I have here is a mass oscillating on a spring with an omega, an angular frequency, which is the same as the angular velocity of this wheel that's rotating. And notice that the green spot on the wheel, it's moving in 2 dimensions. Our mass is only moving in 1 dimension. But if you plot just the y component of the green object, it moves exactly the same as our red mass on our spring. So you can kind of think of the motion of harmonic motion as just being the y component of something that is rotating. And so that's the connection between angular frequency and angular velocity. So the rotational angular velocity is analogous to the angular frequency for oscillation. The phase of rotation is just theta, how far the thing is rotated, which is just the angular velocity times t plus omega naught if we're rotating at a constant velocity. The phase of oscillation for a constant frequency is just omega t plus phi. All right, so hopefully you can see the connection between rotation and harmonic oscillation. And that's the end of our presentation for today.